The commander of the captured Sherman M4A3 sat motionless in the turret, staring at the sight picture through American optics. Outside, in the early morning frost of December 9th, 1944, his crew waited near the tank, smoking captured American cigarettes and wondering what their Oberleutnant was doing in there. They were 15 kilometers behind German lines, in a temporary assembly area near the Belgian town of Elsenborn. The tank had been captured intact 3 days earlier, when its crew abandoned it after track damage during the initial hours of what would become known as the Battle of the Bulge. Oberleutnant Klaus Becker had commanded Panzer Fours for 2 years. He'd fought in Russia, survived Kursk, and made it through the grinding retreat across Ukraine. He knew tanks the way a concert pianist knows a Steinway. He understood the relationship between speed, aim, and accuracy. He knew that you stopped your tank before firing, let the suspension settle, let the gun, sight stabilize, then squeezed the trigger. That was tank gunnery. That was how it worked. That was physics. Except this American tank seemed to violate physics. The device mounted to the gun was labelled in English, Westinghouse Gyro-Stabilizer Mark I. Becker had heard rumours about American tanks having some kind of stabilization system, but he'd dismissed them as propaganda or exaggeration. Soviet intelligence reports mentioned it. Captured American technical manuals referenced it. But nobody he knew had actually seen one work. Now he was sitting in a tank that supposedly could fire accurately while moving at speed. The claim seemed absurd. German tank doctrine, refined through years of combat, was built on a simple principle. You spot the enemy, you maneuver to an advantageous position, you stop, you aim, you fire. The gunner needed a stable platform. The sight picture needed to be steady. Firing while moving meant missing, and missing in tank combat meant dying. Every German tanker learned this in training. Every combat veteran knew it from experience. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Becker had ordered his crew to fuel the Sherman using captured American gasoline. They'd loaded it with the American 75mm ammunition they'd found in a nearby supply dump. Now, with morning light breaking through the winter clouds, he was about to test whether American engineering had actually solved a problem. German engineers said couldn't be solved. The question wasn't just technical curiosity. If American tanks could fire accurately while moving, it changed everything about armoured combat. It meant American tank crews could advance under fire, closing range while engaging targets. It meant they could retreat while fighting. It meant the fundamental tactical assumptions that governed tank warfare might be wrong, or at least incomplete. Becker called down to his driver, a veteran named Hauptmann, who'd survived 3 years on the Eastern Front. Start the engine, we're going to run a test. To understand what Becker was about to discover, you need to understand the state of tank gunnery in 1944. The technology seemed straightforward. A tank gun was essentially a large rifle mounted in a turret. You aimed it using optical sights that magnified the target. You calculated range, adjusted for target movement, and fired. Simple in theory. Vastly complicated in practice. The problem was that tanks moved, and movement created instability. Every bump in the terrain transferred through the suspension to the hull, then to the turret, then to the gun. The heavier the gun, the more it wanted to continue moving even after the hull stopped. This created oscillation, a pendulum effect where the gun barrel would bounce slightly up and down. The oscillation might only last 2 or 3 seconds, but those seconds meant the difference between a hit and a miss. German tanks addressed this through doctrine and training. The driver learned to stop smoothly, minimizing the bounce. The gunner learned to wait for the sight picture to stabilize. Good crews could stop and fire in 4 to 6 seconds. Excellent crews could do it in 3, but even the best crews needed those seconds of stability. The Americans had tried something different. Instead of training their crews to work around the problem of instability, they'd attempted to eliminate the problem entirely through engineering. The gyro-stabilizer was supposed to keep the gun pointed at the target, regardless of what the tank hull was doing. The concept wasn't new. Gyroscopes had been used for navigation and stabilization since the early 20th century. Ships used them to stabilize gun platforms. Aircraft used them for bomb sites. But putting a gyro-stabilizer in a tank presented unique challenges. Tanks experienced violent, unpredictable movement. They rolled over uneven terrain, crashed through obstacles, absorbed recoil from their own guns. Any stabilization system had to handle enormous forces while maintaining precise control. The Westinghouse gyro-stabilizer that Becker was staring at consisted of two main components. The gyroscope itself, spinning at high speed, created a reference point that remained fixed, regardless of how the tank moved. Connected to the gyroscope was a hydraulic system that moved the gun to compensate for hull movement. If the tank pitched forward, going down a slope, the hydraulic system raised the gun barrel to maintain aim. If the tank rolled left, hitting a bump, the system adjusted right. In theory, it was elegant. In practice, German engineers who'd studied captured technical documents said it couldn't possibly work well enough to matter. The hydraulic response time would be too slow. The gyroscope would be too sensitive to shock. The system would add complexity and weight, without providing meaningful combat advantage. Better to stick with proven doctrine. Stop, aim, fire. Becker was about to find out who was right. The Sherman's engine rumbled to life with a sound distinctly different from a German tank. Smoother, quieter, less mechanical violence. Becker had noticed this immediately when they'd first captured the tank. Where a Maybach engine announced its power with aggressive mechanical noise, the American right radial hummed with what seemed like casual indifference. He switched on the gyro-stabilizer using the toggle clearly labelled in English. A gentle whirring sound came from somewhere in the turret. He could feel a faint vibration through the gun controls. The gun, which had been drooping slightly under its own weight when the system was off, lifted fractionally and held position with what seemed like determination. Becker traversed the turret to face a knocked-out German, half-track sitting abandoned about 800 meters away. He centered the sight reticle on the vehicle's engine compartment. Through the periscope sight, he could see the target clearly in the morning light. He told his driver to move forward at moderate speed, maybe 20 kilometers per hour. The Sherman lurched into motion. Becker expected the sight picture to jump around as the tank rolled over the uneven ground. Instead, the target stayed centered in his sight, as if the tank wasn't moving at all. The hull was pitching and rolling beneath him. He could feel it through his seat, through his feet, through every point of contact with the tank. But the gun remained pointed exactly where he'd aimed it. He increased speed. 25 kilometers per hour now, the Sherman bouncing over frozen ruts and scattered debris. The target should have been dancing in his sight, unusable for aiming. Instead, it remained rock steady. The gyro-stabilizer was making thousands of tiny corrections every second, moving the gun fractionally up, down, left, right, compensating for every movement of the hull. The hydraulic system responded faster than human reflexes could match. Becker pressed the firing button. The 75mm gun roared, the familiar shock of recoil transmitted through the turret. He kept watching through the sight as the tank continued moving. The tracer from the armor-piercing round arced across the winter landscape and struck the abandoned half-track dead center in the engine compartment, exactly where he'd aimed. At 25 kilometers per hour, while moving, first shot hit. He told his driver to stop. The Sherman settled, its suspension compressing slightly as momentum bled away. Becker sat in the commander's position, trying to process what he'd just witnessed. In 3 years of combat, he'd never hit a target from a moving tank. Nobody did. It wasn't done because it couldn't be done. Except he'd just done it. He ordered the driver to move. Again, this time faster. 30 kilometers per hour now, the Sherman racing across the frozen field. He selected a different target, a burned-out German truck, perhaps 600 meters distant, centered the sight, felt the gyro-stabilizer holding the gun steady, despite the tank's violent motion. Fired. Another hit. The crew outside had stopped smoking. They were watching the Sherman race back and forth across the field, firing while moving, hitting targets with what seemed like impossible consistency. This shouldn't be possible. It violated everything they knew about tank combat. Becker tried again, this time at an extreme angle, the tank moving laterally relative to the target. Another hit. The gyro-stabilizer tracked smoothly, the hydraulic system compensating not just for vertical movement, but for the complex three-dimensional motion of a tank moving at speed over rough terrain. After 20 minutes of testing, Becker had fired 17 rounds, 14 hits. The 3 misses came when he'd deliberately tried to engage targets beyond effective range or through obscuring terrain. Every shot at combat ranges, every shot where he'd properly aimed and fired, had hit, not near misses. Direct hits. He climbed out of the Sherman and lit one of the captured American cigarettes. His hands were shaking slightly, though not from cold. His crew gathered around, waiting for his assessment. What Becker told them would challenge everything they believed about armoured warfare. The stabilizer works. It actually works. You can fire accurately while moving at full speed. The silence that followed wasn't disbelief. It was the sound of experienced tankers, realizing that they'd been fighting with a fundamental disadvantage they hadn't known existed. The gyro-stabilizer didn't just work, it changed the tactical calculus of tank combat in ways that were immediately obvious once you'd seen it function. Becker's crew spent the rest of that morning discussing the implications while continuing to test the Sherman's capabilities. Each test revealed another advantage they hadn't considered. In German tanks, engaging a target required a specific sequence. The commander identified the target and gave the range. The gunner traversed to the target. The driver stopped the tank. The gunner waited for oscillation to settle, then fine-tuned his aim. The loader confirmed ammunition type. The gunner fired. The entire sequence took at minimum 4 to 6 seconds with a well-trained crew. 4 to 6 seconds doesn't sound like much, but in combat, it's an eternity. During those seconds, the enemy tank is also trying to complete their firing sequence. Whoever fires first usually wins. More critically, during those seconds while you're stopped and aiming, you're a stationary target. The enemy knows roughly where you are, and their gunners are trying to put a round through your armour. The Sherman, with its gyro-stabilizer, eliminated the need to stop. The gunner could keep the sight on target while the tank manoeuvred. When the commander gave the fire command, the gunner could engage immediately. The firing sequence collapsed from 4 to 6 seconds down to essentially instantaneous. Meanwhile, the Sherman remained a moving target, harder to track, harder to hit. Becker had his driver execute a tactical scenario they'd run countless times in training and combat. A German tank spotted an enemy at 800 meters. The German tank stops to engage. In the 4 seconds it takes to settle and aim, the enemy tank covering ground at 25 kilometers per hour has moved 28 meters closer and can fire while doing so. By the time the German gunner is ready to fire, the enemy has already taken their shot and is now at 770 meters, inside optimal combat range for their gun. The mathematics were brutal. The stabilizer didn't just allow the Sherman to fire while moving it, compressed the engagement timeline so dramatically that German tanks lost the initiative before they could even take the first shot. Hauptmann, the driver, understood immediately. He'd survived 3 years on the Eastern Front by being better than the enemy, faster than the enemy, more aggressive than the enemy. Now he was looking at a machine that could be aggressive in ways German doctrine said were impossible. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. We've been fighting with one hand tied behind our backs, Hauptmann said quietly. Every time we stop to shoot, we're giving them a free shot at a stationary target. They don't have to stop. They can keep moving, keep shooting, and we can't. Becker was already thinking through the tactical implications for the larger battle raging around them. The offensive, later to be called the Battle of the Bulge, had caught the Americans by surprise. German tanks had achieved local superiority in several sectors. But that superiority assumed tactical parity, tank for tank. If American Shermans could fire effectively while German tanks couldn't, that changed force calculations dramatically. A German Panther might have better armor and a more powerful gun than a Sherman, but those advantages only mattered if the Panther could bring its gun to bear effectively. If the Sherman could fire while advancing and the Panther had to stop to shoot, the Sherman gained seconds of advantage. In a close-range engagement, seconds were decisive. The gyro-stabilizer also changed the psychology of tank combat. German tank doctrine emphasized careful positioning, utilizing range and cover, fighting from static positions when possible. This made sense when your tank needed to be stationary to fire accurately. But it meant German tanks were often defensive, reactive, waiting for opportunities rather than creating them. American doctrine, built around the capabilities of stabilized guns, could be more aggressive. Sherman crews could advance under fire, confident they could engage targets while moving. They could retreat while fighting, maintaining suppressive fire even during withdrawal. They could maneuver aggressively, using speed and motion as active defenses while still maintaining offensive capability. Becker pulled out a small notebook he carried for tactical observations. He began writing down everything he'd learned, knowing this information needed to reach higher command immediately. But as he wrote, a troubling realization emerged. How many other American advantages had German intelligence missed or dismissed? The stabilizer wasn't a secret. Captured Sherman manuals mentioned it. Soviet reports discussed it. American technical specifications included it. But German analysis had concluded it was insufficiently developed to matter in combat. That analysis was catastrophically wrong. What else were they wrong about? The Sherman's construction suddenly made more sense through this lens. German engineers mocked American tanks for being simple, crude, less sophisticated than German designs. But what if that simplicity was intentional? What if the Americans had deliberately chosen reliability and ease of production over technical sophistication because they knew the gyro-stabilizer gave them a tactical advantage that outweighed raw specifications? A Sherman couldn't match a Panther's armor or gun, but it didn't need to. It could engage while moving, fire first, maneuver aggressively, and maintain fire during withdrawal. Those capabilities, enabled by the stabilizer, compensated for deficiencies in armor and firepower. The Americans hadn't built an inferior tank. They'd built a different kind of tank for a different kind of warfare. Becker's gunner, a veteran named Schmidt who'd fought in North Africa before Russia, climbed into the Sherman's turret to examine the stabilizer system more closely. He emerged 20 minutes later with a German technical manual that had been distributed to tank units months earlier. The manual included a section on American tank equipment, including the gyro-stabilizer. The assessment concluded that stabilization systems added complexity without significant combat value, and that German tanks' superior optics and training made such systems unnecessary. Schmidt held up the manual and pointed to the conclusion. This is complete nonsense. That stabilizer is the most effective gunnery advancement I've seen in this entire war. Whoever wrote this assessment never actually tested one, or they lied about the results. The distinction mattered. If German technical intelligence had simply failed to test captured stabilizers properly, that was incompetence. But if they'd tested them, seen them work, and still dismissed them as insignificant, that suggested something more troubling. An institutional inability to accept that American engineering might be solving problems. German engineering had declared unsolvable. German tank development in the war's early years had been remarkably successful. The Panzer III and IV were excellent designs. The Panther, despite its mechanical problems, had formidable capabilities. German optics were genuinely superior. German guns were more powerful. But somewhere in the progression from early success to mid-war dominance, German tank development had become inward-looking, focused on making German tanks better, according to German definitions of better, rather than asking what tanks needed to do on a modern battlefield. The Americans had asked a different question. Not, how do we make a better tank, But how do we make tanks that win battles? The distinction led to fundamentally different solutions. German tanks kept getting heavier armor and bigger guns because those specifications looked impressive on paper. American tanks got gyro-stabilizers and better logistics because those advantages actually mattered in combat. Becker knew he needed to get this information to division headquarters immediately, but he also knew what the response would likely be. Staff officers would read his report, note the observations, and then file it away with all the other tactical reports that arrived daily from the front. The information might eventually reach someone who could act on it, but by then it would be too late to matter for this offensive, possibly too late to matter for the war. German tank development cycles were measured in years. Even if High Command immediately recognized the importance of stabilization systems and ordered their development, German tanks wouldn't have working stabilizers until 1946 at the earliest. The war would be over by then, one way or another. Still, he wrote the report, detailed observations, specific test results, tactical implications, recommendations. He sent it through normal channels with a request for urgent review. Then he and his crew disabled the captured Sherman. They couldn't risk it being recaptured by American forces in working condition, and returned to their regular Panzer IV. Sitting in his familiar command position, looking through familiar optics, feeling the familiar vibration of the Maybach engine, Becker felt like he was sitting in an obsolete machine. The Panzer IV was a good tank, proven in combat, reliable enough when properly maintained. But it was a tank designed for a previous era of warfare, an era when both sides fought under the same constraints. The Americans had broken free of those constraints. German tanks hadn't. The offensive would continue for another month, ultimately failing to achieve its objectives. German tanks would achieve some local tactical victories, particularly in the war's opening days when surprise and force concentration worked in Germany's favor. But in sustained engagements, where tactics and technology mattered more than surprise, American tanks demonstrated consistent advantages that German crews couldn't overcome, through skill or courage alone. Some of those advantages were obvious: American numbers, American logistics, American air superiority. But some were subtle, technical, the kind of advantages that didn't show up in intelligence assessments or situation reports. The gyro-stabilizer was one of those invisible advantages, unremarkable until you experienced its effects directly, then impossible to ignore. Becker would survive the Battle of the Bulge and the subsequent retreat into Germany. He would surrender to American forces in April 1945, ending his war as a prisoner rather than a casualty. In post-war interviews, he would talk about many things: the Eastern Front, tactical evolution, the decline of German armored forces. But whenever he discussed American tanks, he would mention that morning in December when he test-fired a captured Sherman and discovered that everything he'd known about tank gunnery was incomplete. The gyro-stabilizer, he would say, was the weapon we never saw coming because we'd convinced ourselves it couldn't matter. We thought we were fighting with superior tanks. We were actually fighting with obsolete doctrine against an enemy who'd solved problems we didn't know existed. That's not a fight you can win through courage or determination. That's a fight you've already lost before it begins. The technical specifications of the Westinghouse gyro-stabilizer told a story that German engineers should have paid attention to, but largely ignored. The system wasn't particularly exotic. It used proven technology applied in a novel way. What made it remarkable wasn't that it existed, but that American designers had prioritized its development and deployment when German designers had decided similar systems weren't worth pursuing. The gyroscope at the heart of the system spun at approximately 20,000 revolutions per minute, creating a stable reference plane that remained fixed regardless of tank movement. The gyro was mounted on gimbals that allowed it to maintain orientation even as the tank pitched, rolled, and yawed across rough terrain. Connected to the gyroscope were electrical pickups that detected any deviation between the gyro's orientation and the gun's actual position. When the tank hit a bump and the hull pitched forward, the gyroscope remained level. The electrical pickups detected that the gun, physically connected to the pitching hull, was now pointing downward relative to the gyroscope's reference plane. This signal went to a hydraulic control valve that released pressure to actuators connected to the gun. The actuators raised the gun barrel, compensating for the hull's pitch. The entire process happened in milliseconds, faster than human reflexes could respond. The system had limitations. It only stabilized in the vertical plane. The gun could move up and down to compensate for hull pitch, but the gunner still needed to manually traverse left and right to follow moving targets. The stabilizer also couldn't compensate for extreme shocks like hitting a large obstacle or firing the main gun. During firing, recoil momentarily overwhelmed the system, and it took a second or two to re-establish stable tracking after each shot. But these limitations didn't diminish the system's fundamental value. Even partial stabilization transformed gunnery effectiveness. A gunner who only had to manually track in one dimension while the stabilizer handled the other could engage targets far more quickly and accurately than a gunner manually tracking in both dimensions while also dealing with hull motion. German technical teams had actually captured their first Sherman with a working stabilizer in Tunisia in early 1943, more than 18 months before Becker's test in Belgium. The captured tank was shipped to the Waffenamt testing facility at Kummersdorf, where German engineers spent weeks examining every aspect of its design. Their report acknowledged that the stabilizer functioned as designed, but concluded that its combat value was minimal. The reasoning behind this dismissal revealed a fundamental misunderstanding of how the device would be used in practice. German testers evaluated the stabilizer's precision compared to a perfectly stationary tank with an experienced gunner. They found that the stabilized gun moving across rough terrain was slightly less accurate than a stopped tank with optimal aim. This was true but irrelevant. The proper comparison wasn't stabilized while moving versus stopped and perfectly aimed. It was stabilized while moving versus unstabilized while moving. By that metric, the advantage was overwhelming. The German report also noted that the stabilizer added approximately 227 kilograms to the tank's weight, consumed electrical power, required additional maintenance, and represented a potential point of failure. All true, but the report failed to quantify the tactical value of being able to fire effectively while moving, probably because the evaluators never tested the system in realistic combat scenarios. This pattern technically accurate evaluation that missed strategic significance appeared repeatedly in German assessments of American equipment. German reports correctly noted that Sherman armor was thinner than Panther armor, that the 75mm gun was less powerful than the German 88mm, that American optics had lower magnification than German Zeiss optics, all factually correct, all strategically misleading because they evaluated individual components rather than system effectiveness. A tank isn't a collection of specifications. It's a weapons system that must function as an integrated whole under combat conditions. The Sherman was designed as a system where each component supported overall combat effectiveness. Thinner armor meant lower weight, which meant better mobility and less strain on the drivetrain. The less powerful gun was adequate for most targets and allowed faster firing rates. Simpler optics were easier to maintain and less susceptible to shock damage. And the gyro-stabilizer multiplied the effectiveness of every other system by allowing the tank to fight while maneuvering. German tank design philosophy, by contrast, optimized individual components, often at the expense of system integration. The Panther had excellent armor, but the weight stressed the drivetrain to failure. It had a powerful gun, but the long barrel made maneuvering difficult in confined terrain. It had superb optics, but they required perfect alignment that combat conditions disrupted. Each component was excellent in isolation. Together, they created a tank that was less than the sum of its parts. The irony was that German engineers understood systems integration perfectly well in other contexts. The Luftwaffe's aircraft development, particularly in the early war years, showed sophisticated understanding of how to balance competing requirements. The Messerschmitt Bf 109, optimized different factors for different roles: speed versus maneuverability, firepower versus weight, range versus performance. But somehow, this system's thinking didn't transfer to tank development, where the focus remained on making each specification better rather than making the complete system more effective. By late 1944, when Becker was testing the captured Sherman, German tank crews were beginning to understand these distinctions through brutal experience. They were fighting American tanks that could maneuver aggressively, fire effectively while moving, and maintain operations day after day with minimal maintenance. Meanwhile, German tanks were increasingly sidelined by mechanical failures, unable to maneuver effectively due to fuel shortages, and forced into defensive positions because their gunnery doctrine required static firing positions. The strategic impact of the gyro-stabilizer extended beyond individual tank engagements. At the operational level, stabilized gunnery enabled different approaches to armored warfare that German forces couldn't effectively counter. American tank units could conduct movement-to-contact operations where they advanced aggressively toward enemy positions while maintaining the ability to engage targets as they appeared. German units conducting similar operations had to halt and establish firing positions before engaging, slowing their advance and allowing enemies to escape or reinforce. During defensive operations, American tanks could conduct fighting withdrawals, where they retreated while maintaining suppressive fire on advancing enemy forces. German tanks attempting similar maneuvers had to stop to fire, making them vulnerable to being overrun or encircled. The stabilizer transformed retreat from a vulnerable operation into a tactical option that maintained combat effectiveness. Tank versus tank combat statistics from the Western Front in late 1944 and early 1945 showed patterns that German commanders struggled to explain. In engagements where German tanks had apparent advantages, better positions, superior cover, longer-range guns, they still suffered higher loss rates than expected. After-action reports attributed this to American numerical superiority or air support, which were certainly factors. But buried in the detailed engagement reports were consistent observations. American tanks engaged while advancing, American tanks fired while maneuvering, American tanks maintained fire during withdrawal. These observations described the tactical advantages enabled by gyro-stabilization, but German analysts didn't connect them to a specific technical capability. They attributed American aggressiveness to doctrine or training rather than to technology that enabled aggressive tactics. This analytical failure meant German forces never developed effective counter-tactics to exploit the stabilizer's JUMO size. Limitations. The limitations were real and exploitable. The stabilizer only worked in one axis, meaning skilled German gunners could potentially track laterally moving Shermans more effectively than Shermans could track laterally moving German tanks. The stabilizer couldn't compensate for extreme terrain features, meaning combat in very rough terrain partially negated its advantages. The system could be damaged by shock, meaning a near miss from artillery might disable the stabilizer even if the tank remained mobile. But exploiting these limitations required understanding they existed. German tactical doctrine never evolved to specifically counter stabilized gunnery, because German intelligence never adequately communicated that stabilized gunnery was a significant factor in American combat effectiveness. Individual crews like Becker's learned through direct experience, but their observations didn't propagate effectively through the command structure. This intelligence failure had roots in organizational culture. German military culture valued technical sophistication and engineering excellence. American equipment that appeared crude or simple was dismissed as inferior by default. When German engineers examined the Sherman and found it was simpler than a Panther, they concluded the Sherman was therefore worse. They didn't seriously consider that American engineers might have deliberately chosen simplicity for tactical reasons. The Sherman's transmission provided another example of this dynamic. German tanks used complex multi-speed transmissions with synchromesh gears, similar to those in high-performance automobiles. American tanks used much simpler transmissions with fewer gears and basic gear teeth. German engineers noted this as evidence of American technical inferiority. They didn't consider that simpler transmissions were easier to manufacture, easier to maintain, more reliable in combat, and adequate for tactical needs. The Sherman didn't need 7 gears because it didn't need to achieve the high road speeds German doctrine emphasized. It needed to be reliable, and simplicity delivered reliability. By spring of 1945, as the war in Europe entered its final weeks, the technological gap between German and American tanks had widened to the point where German armor was increasingly irrelevant to battlefield outcomes. German tanks were being destroyed by mechanical failures, fuel shortages, and lack of trained crews more often than by direct combat. The few German tanks that remained operational faced American forces that had refined their tactics around the advantages their technology provided. American tank platoons in the war's final months operated with an aggressiveness that would have been suicidal in 1942. They advanced rapidly across open ground, engaging targets while moving, using speed and firepower to overwhelm defensive positions before defenders could establish effective fire. This wasn't recklessness. It was doctrine built around technological capabilities, particularly gyro-stabilized gunnery, that allowed offensive maneuver and effective fire to happen simultaneously. German defenders, even experienced veterans with good equipment, struggled to counter these tactics. Their doctrine still emphasized establishing firing positions and engaging from static locations. Against enemies who could fire effectively while moving, this put them at an immediate disadvantage. By the time German gunners acquired targets and prepared to fire, American tanks had often already taken their shots and were maneuvering to new positions. The after-action reports from this period make fascinating reading for anyone interested in how technology shapes tactics. German reports consistently noted American aggressiveness and rapid maneuver, but interpreted these as signs of desperation or poor training. American reports noted German defensive competence, but also mentioned that German tanks seemed hesitant to maneuver during engagements, preferring to fire from fixed positions. Neither side fully articulated what was happening. American technology enabled aggressive tactics, while German doctrine, developed for unstabilized gunnery, constrained tactical options even when better equipment became available. The Panther and Tiger tanks Germany fielded in late war had superior guns and armor compared to Sherman's, but German crews never received stabilizers that would have let them fully exploit those advantages through aggressive maneuver. German tanks remained tactically constrained by doctrine designed for earlier technology. American tanks, though individually inferior by most specifications, operated within a tactical framework that maximized their actual capabilities. Klaus Becker's report about the captured Sherman's gyro-stabilizer eventually reached higher command levels, though exactly when and how remains unclear from surviving records. What is clear is that by the time German tank designers fully understood the stabilizer's significance, they lacked the industrial capacity, time, and resources to develop competing systems. Germany in early 1945 was struggling to produce enough conventional tanks to replace losses. Developing new stabilization technology was impossible. Some German engineers did begin preliminary design work on stabilization systems in the war's final months. Documents captured after Germany's surrender included sketches and calculations for gyroscopic gun stabilizers, similar in concept to the American system. But these were paper exercises, engineering speculation about what might have been possible under different circumstances. None of the designs progressed beyond initial concept work. The tragedy for German tank crews was that they were fighting a technological war with outdated tools, not because German engineering was incapable of producing better tools, but because German military leadership had failed to recognize which technologies actually mattered. They'd prioritized armor thickness and gun caliber, specifications that looked impressive in comparison charts. They'd ignored or dismissed stabilization, reliability, and maintainability factors that determined whether tanks actually functioned effectively in sustained combat. This wasn't unique to tanks. German military technology across many domains showed similar patterns. The Luftwaffe developed sophisticated aircraft with impressive performance specifications, but complex maintenance requirements that reduced operational availability. The Kriegsmarine built submarines with advanced sensors, but vulnerability to Allied countermeasures they hadn't anticipated. The Wehrmacht fielded excellent infantry weapons, but failed to motorize logistics sufficiently to support operations. In each case, German engineering excellence produced technically impressive equipment that failed to deliver proportional combat effectiveness. American equipment, often simpler and less impressive on paper, delivered superior combat effectiveness through better systems integration, easier maintenance, and design choices that prioritized tactical utility over specification superiority. The gyro-stabilizer embodied this difference in approaches. German engineers could have developed stabilizers. The basic technology wasn't beyond their capabilities, but they didn't, because their evaluation process emphasized technical sophistication over tactical utility. American engineers developed stabilizers because they asked what tank crews needed to be more effective in combat and then engineered solutions to those needs. This difference in design philosophy extended beyond equipment to organizational culture. American military organizations were relatively comfortable with feedback from combat units influencing design decisions. German organizations maintained stronger separation between designers and users, with engineers generally having more authority than field commanders in determining equipment characteristics. When American tank crews reported problems, those reports often led to design changes. When German tank crews reported problems, those reports more often led to revised tactics or additional training rather than engineering modifications. The stabilizer's development history illustrated this pattern. American ordnance officers had worked closely with Westinghouse engineers throughout the development process, providing feedback from test crews, adjusting specifications based on practical requirements, and iterating the design based on field observations. The result was a system that worked well enough to deploy widely, even if it wasn't perfect. German engineering culture would likely have kept a similar system in development longer, refining it toward theoretical perfection before deployment, by which time the tactical situation might have evolved beyond the system's original requirements. By war's end, American forces had deployed gyro-stabilizers across thousands of Sherman tanks. The system had become standard equipment, expected by crews, integrated into doctrine, taken for granted as part of how tanks fought. German forces, meanwhile, were still operating under doctrines that assumed gunnery required stationary firing positions, not because that assumption was correct, but because their tanks lacked the technology to make it incorrect. The post-war period saw interesting developments in tank stabilization technology. Soviet forces, having captured both German and American tanks during the war, studied both approaches to tank design. Their post-war tank development clearly showed American influence, with emphasis on reliability, maintainability, and integrated systems, rather than maximum performance specifications. Soviet tanks incorporated stabilization systems in the late 1940s, recognizing the tactical advantages they provided. Western tank development also embraced stabilization as standard. British, French, and American tanks of the 1950s and beyond included increasingly sophisticated stabilization systems, eventually achieving full two-axis stabilization that controlled both vertical and horizontal gun movement. These systems became fundamental to modern tank design, so basic that contemporary tankers would find it bizarre that tanks ever fought without stabilization. German post-war tank development, first in West Germany as the Bundeswehr formed, showed clear evidence of lessons learned from wartime failures. West German tanks like the Leopard 1, developed in the 1960s, emphasized reliability and maintainability alongside performance. They included stabilization systems as standard equipment. The design philosophy had shifted from optimizing individual specifications toward integrating components into effective combat systems. Klaus Becker, after his release from prisoner of war camps in 1946, returned to civilian life in Germany. He worked as a mechanical engineer for various industrial firms, eventually retiring in the late 1970s. In a 1982 interview for a German military history journal, he reflected on his wartime experience testing the captured Sherman. "We thought we were more sophisticated," he said. "We thought our tanks were better because they had better armor and bigger guns. But the Americans understood something we didn't. They understood that the best tank isn't the one with the best specifications. It's the one that wins battles. Their stabilizer gave them an advantage that all our armor and firepower couldn't overcome. They could fight in ways we couldn't, and that decided the war more surely than any single battle." The interviewer asked whether German engineers could have developed similar stabilizers if they'd started earlier in the war. Becker's response was thoughtful. "Technically? Of course. German engineers were excellent. But we wouldn't have, because we were asking the wrong questions. We were asking how to make tanks more powerful, more heavily armored, more technically impressive. The Americans were asking how to make tanks more effective in combat. Those seem like similar questions, but they lead to completely different answers. The stabilizer was the answer to a question we never asked." The lessons from the Gyro-Stabilizer story extended well beyond tank warfare. They spoke to fundamental questions about military technology, engineering philosophy, and how organizations innovate under pressure. German forces had lost technological superiority, not because they lacked capable engineers or advanced technology, but because they'd optimized for the wrong criteria. This pattern has appeared repeatedly in military history. The best weapon isn't always the most powerful or the most sophisticated. It's the weapon that best matches tactical requirements, logistical realities, and operational doctrine. Technologies that look impressive in laboratory demonstrations or specification comparisons may fail in combat if they don't integrate well with how forces actually fight. The gyro-stabilizer succeeded because American designers understood this principle. They didn't try to build the most sophisticated stabilization system possible. They built a system that was good enough to provide tactical advantage, simple enough to manufacture widely, reliable enough to function in combat, and maintainable enough to keep operational. It wasn't perfect. It was effective. In warfare, effectiveness matters more than perfection. German tank crews who encountered American forces in late 1944 and early 1945 faced enemies who could do things German doctrine said were impossible. They faced tanks that fired accurately while moving, that advanced aggressively while maintaining suppressive fire, that withdrew while fighting. These capabilities weren't magic. They were engineering solutions to tactical problems. Solutions that German engineers had dismissed as insufficiently sophisticated to matter. The cost of that dismissal was measured in lost battles, destroyed tanks, and casualties that might have been prevented. It's impossible to calculate exactly how many engagements were decided by American stabilizers, but the cumulative impact across thousands of tank actions was significant. Technology that shifts tactical advantage even slightly, when deployed across entire armies over months of combat, shapes strategic outcomes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.